Bueno, buenas tardes o buenos días para todos y todas acá en Argentina. Hoy vamos a tener la segunda charla del ciclo de charlas de la Comisión de Tectónica, de la Asociación Geológica Argentina, la ComTec. Bueno, en esta oportunidad nos va a presentar voy a hacer la introducción un poco ahora en español, les podemos pasar a inglés porque, bueno, va a haber gente también conectada desde otros lugares que hemos enviado el mail de aviso. Bueno, Michaël, él hizo, o sea, se licenció como geólogo y obtuvo su máster en Francia y después se mudó a Alemania para hacer doctorado dentro del GFZ en Potsdam. Su doctorado estaba dentro de un proyecto de cooperación internacional entre Alemania y Argentina para estudiar la cordillera de los Andes, el proyecto Strategy, estudiar la cordillera de los Andes desde distintos puntos de vista, desde la parte climática, la parte de riesgo geológico y la parte tectónica. Y él, puntualmente, se focalizó en la parte de modelado geodinámico para entender cómo es la deformación vinculado a la orogenia andina. Entonces, bueno, ahora Mika nos va a presentar parte de su proyecto y ahora hago la introducción en inglés antes de que comience. So, good afternoon to everyone and good morning here in Argentina and Chile. So, we're gonna introduce Michaël Pons for our second talk in the ComTec lecture series. So, Michaël, he will present some of his work he was doing during his PhD in the strategy project. He earned previously his bachelor and master in degrees in France, but then he moved to Germany, and he was doing his PhD under the strategy project in the GFZ in Potsdam, Germany. And he was focused mostly in geodynamic modeling to understand the Andean deformation. But nowadays he's a postdoctoral researcher at GFZ, and he's trying to understand the global tectonics also by means of geodynamic modeling. So, Mika, it's nice to have you here, and thank you for joining us for this lecture. Thank you.
So, thank you, Matthias. Thank you also all the organizers for inviting me and having me for this talk. So I'm really excited to share with you some of my PhD research on the geodynamics of the Central Andes. And also I would like to extend a big thank you to all my collaborators and in Argentina, gracias. Over the next 30 minutes, I will walk you through some of the key results in my research. And so first, I would like to have a look at the Andes, and many of you are going to probably know what I'm going to discuss in this next slide. But we can actually divide the Andes into three distinct segments. A northern segment, a central, and a southern Andes segment. And so we could divide each of those segments by where we have the subduction of an oceanic ridges. In the north, in between the north and the central segment, we have the subduction of the Nazca ridges here. And in the central to the southern Andes segment, we have the subduction of the Juan Fernandez ridge. So, and in the central domain, we have the formation of the Altiplano Puna Plateau, which is a significant orogenic plateau. So, overall, the subduction of the Nazca plate beneath the South American plate is what drives the uplift and the shortening of the Andes. And so an example of these ridges, a bit more details, for example, the Juan Fernandez ridge, which is actually formed by a hotspot, has been subducted beneath the South American plate. But because of the angle of the subduction, of the convergence between the Nazca and the South American plate, and the orientation of the ridge itself. The Juan Fernandez ridge has actually shifted its position relative to the continent margin. So about 40 million years ago, the ridge was located around 20 degrees south in the Central Andes, and today the ridge is located at the latitude of the Sierras Pampeanas, around 33 degrees south. And the higher buoyancy of the ridge with the long-term subduction and the westward motion of the South American plate has led to the development of flat slab of subduction, like the one we can see at present day, where at the latitude of the Sierras Pampeanas. So when we look at the Andes, we can notice that each segment has a distinct topographic characteristic. In the north and southern Andes, the average elevation is usually lower, while in the central Andes, we have a prominent altiplano orogenic Puna plateau, which therefore has much higher elevation. Interestingly, if we compare the average elevation of the orogen with the average elevation at the trench, we see that they are anti-correlated. So in the northern and southern segment at the trench, the average elevation is actually higher, and in the central Andes, we have a much deeper trench. And this difference in trench topography are also influenced by the amount of sediment that is transported to the trench from the orogen. In the northern and southern Andes, we have high flux of sediments, and this is due to efficient erosion coming from the lush rainforest in the north, or the glacial erosion in Patagonia, for example, in the south. In contrast, the central Andes receive almost no sediments to the trench due to the extreme arid conditions that we observe, such as, for example, in the here at the Atacama Desert. And one of the key consequences of this variation in the sediment flux into the trench is that they can impact of the stress is being transferred between the oceanic plate, subducting plate, and the overriding plate, continental plate above. In areas with more sediments, the plate interface tend to be more lubricated, so resulting in a lower coupling. Those sediments can carry more water, those porous sediments can carry more water deeper into the trench, which result in an increase of pore pressure and a decrease of the strength of the interface. Conversely, where there is less sediments, we tend to see higher coupling and therefore a greater magnitude of shortening. So as a result of this difference of coupling, the amount of shortening magnitude in the Andes can vary quite significantly. In the north and in the south, we can have around 50 kilometers of shortening from those compilation, whereas in the central part, it can exceed 300 to 400 kilometers of shortening. And the previous study, such as the one of Lamb and Davis 2003 or Sobolev and co-authors 2005 and 2006, have attempted to quantify this coupling and have demonstrated how the shear stress at the plate interface changes with latitudes. In this presentation, I'm going to focus on the two different areas. One will be along the central Andes, where we will take into account this different coupling condition of that area, and examine how the subduction dynamic have influenced the shortening over the last 30 million years. The other focus will be on the southern central Andes, where we will explore how the Pampean flat subduction observed today influence the change in deformation style in the foreland. So let's have a look to the central Andes. Here is a cross-section from previous cross-section compilation that I have tried to compile and show you here. And so overall, what you can see is that we can split the continental domain into two main distinct areas, the plateau area and the foreland area. And so most of the deformation occur in the eastern Cordillera, and in the Sub-Andean ranges, where we have also the undertrusting of the Brazilian cratonic shield. And under the plateau area, you can see that most of the mantle lithosphere, which is actually quite a strong part of the lithosphere, has been removed, delaminated. We can also look how the deformation rate has been changing over time. And so at the beginning, 46 million years ago, we started deforming the Western Cordillera, and then we have a migration of the deformation to the plateau domain and the Eastern Cordillera mostly. And finally, in the last 12 million years, most of the deformation in the Central Andes, around 21 degrees south, is accommodated in the Sub-Andean ranges in the foreland. But we can also examine the rate at which the Andes have shortened over time by integrating all those different signals across all those different areas. And so you can see that most of the Andes start to form really around the present Andes. Elevation starts mostly to form around 46 million years ago. And then we have some phases of acceleration of the shortening, and this is due to the passage of the flat subduction that we have seen previously from the migration of the Juan Fernandez Ridge to the south. And then we have some period of steady shortening, and then in the last 15 million years, we have at 15 and 4 million years, we have some pulsated phase of shortening. And so I was really interested to understand what led to this pulsative phase of shortening, as well as the acceleration that we observe, for example, here at 33 million years ago. So what controls the variation in the shortening rate, but also what is the role of the flat subduction in the shortening of the Central Andes. And so for this, I used numerical modeling as a tool. So I set some numerical geodynamic models that simulate the Earth physics coupled of a conservation equation. And this model also incorporates the rheological behavior of the rocks by including laws for plasticity, which simulate, for example, brittle deformation, and also viscous creep, which allow to simulate ductile deformation, a bit like dulce de leche. For this work, I used the code aspect, the geodynamic code aspect. And so the first model is a 2D geodynamic model of the Central Andes. And in this model, I used the reconstructed geometry of the South American plate in the Central Andes around 35 million years ago. And then I start by prescribing plate velocity to each of the plate, the oceanic and the continental plate, at 35 million years ago, as well as I prescribe different composition in order to get the flat subduction prescribed, the flat subduction similar to the present-day Pampean flat slab that we observe. And finally, I let the model evolve on its own. So the oceanic plate is going to be driven by its own weight, while I keep prescribing the westward absolute motion of the South American plate. And here is 2 centimeters, for example, which is an average for the last 35 million years. So we can look at the model evolution, and you can see that we begin with flat subduction, but after some time, the slab begins to free fall into the upper mantle and steepens. Pieces of the continental mantle are scraped off and removed from the avoiding plate, and here the model is restarting, so I looked over it, so you can have a better, so you can see better. And when the slab reaches the lower mantle, it begins to stagnate. Trench retreat actually is mainly driven by the motion of the South American plate rather than the rolling back of the slab. And this is because of the high interplate coupling that we have in the Central Andes. And the slab begins to buckle, like here. The continents then, like we say, delaminate, and when the slab free fall into the mantle after each buckle, so free fall and steepens into the mantle, it causes the oceanic trench to be blocked or to slow down its retreat. It's during this slowdown, like now, and blocking of the oceanic trench that the deformation at the surface intensify, and as the overriding plate continue to move towards the trench. The deformation then migrate all the way to the foreland, and ultimately leads to the undertrusting, like now, of the Brazilian cratonic shield. So we can summarize and break down the model evolution into 4 main stages. The first stage involves the flat slab free fall and steepening into the asthenosphere mantle. And the remaining free and the steepening and removing of the continental mantle lithosphere weakens the overriding plate. And the remaining free stage form a buckling cycle where the slab end up stagnating into the mantle transition zone or above the lower mantle, which causes it to fold. And finally, because the trench keep moving towards the west, the slab end up again free falling and steepening behind the previous buckle, and the new buckling cycle can restart. And whenever the slab is free falling into the asthenosphere, that's usually when we observe that we have the most of the shortening, because during this phase, the trench is blocked and the overriding plate continue to move towards the trench, which therefore leads to an increase of shortening at the surface. So now I will show you 2 more variations of this reference model that you can see here in the center. And this variation, in this variation, I will adjust the continental plate velocity, because in reality, the absolute velocity of the continental plate has changed over time from 3 to 4 centimeters around 35-40 million years ago, down to 1 centimeter per year at present day. And so you can see in this resulting model evolution that for different plate velocity, we also get different regimes of subduction. When the continental plate move quickly towards the trench, the slab does not have time to fold and buckle, but we see a significant amount of shortening on the overriding plate in the Eastern Cordillera and in the foreland. In the other hand, when the plate velocity is about 1 centimeter per year, the slab falls and piles up on itself, and we have almost no continental deformation, only just after flat slab steepening. And overall, we can identify 3 different regimes. The first regimes on top with the fast plate convergence of plate velocity is often referenced as a slab anchoring regime. And in the low plate velocity regime, this regime is often also referenced as piling regime. Here, I suggest here we propose an intermediate regime, which isn't as commonly referenced, and that I call here free falling of the slab, slab buckling, and steepening regime. So maybe there might be a way to get a shorter name. For example, in a way, this different subduction regime can be compared to our everyday experience of life. In the high velocity regime, it could be compared to, for example, like when you are squeezing a toothpaste onto your toothbrush, and the fast motion of your hand, which represents the trench motion, keeps the path straight and prevents it from buckling. In contrast, in the low velocity regime, it is more like watching honey slowly going down, sinking, dripping from a spoon that you maintain stagnant. So the honey fold and pile on itself. And the reference model that we have in the center, which show an intermediate regimes, is more like pulling on a Twix bar. The caramel falls behind each buckles as you move slowly from one side of the Twix to the other one. And so we can, in order to determine which of this regime is most likely occurring in Central Andes, we can compare the amount of shortening from the geological data compilation of Onorankin and with the shortening that we are getting from our model. And so in the high velocity regime, the slab anchoring model produced too much deformation overall. The foreland under thrusting also happens, big foreland under thrusting of the Brazilian Tectonic shield begins too early in the model evolution and leading to too excessive shortening compared to what we see from the geological record. For the honey regime or the low velocity plate velocity regime, the slab is piling and the deformation is much less efficient and remains mostly confined to the plateau domain with a limited propagation of the deformation to the foreland. But looking at the reference model, we see that the shortening rate appears to match closely the geological data. And I will take a look closer to this signal. And you see that the model begins to increase in its shortening around 35 million years ago, which is during the free falling of the slab after the free falling of the flat slab. In every of the model, we try to overestimate the shortening after the passage of the flat slab, which could be a result of the 2D assumption of our model. Which therefore it becomes too intense. And then we have a steady phase where we have a bit of up and down, as suggested also by the geological data compilation. And then around the 16 and the 5 million years, we have those pulses of shortening increases. And so we can look at the signal by looking at how much shortening we have through the plateau domain versus how much shortening we have by the undercrusting of the Brazilian Tectonic shield. And you see that most of the deformation happen first in the plateau domain and in the eastern Cordillera. And then around 12 million years ago, we have a prominent deformation coming from the underthrusting of the Brazilian Tectonic shield. And this underthrusting is occurring in two phases. One around dominant phase around like 13 million years ago, and then another one in our model around 5 million years ago. And then we decrease again the shortening rate to arrive to some present day value. So this pulse of shortening rate occurs during phase of slab free falling and steepening, either just after the flat slab or before each buckling cycle. And this process effectively blocks the trench, causing the South American plate to collide with the trench, which in turn intensifies the deformation. And as you see here in green, during this free falling phase. So now, to give you a sense of how the topography evolves during the model run, I will now show you a landscape evolution model spanning the whole model evolution. The image below the landscape evolution model will remain static. This is a geodynamic model at the last stage of this model. It represents the final stage then of the geodynamic model. And the animation gives you a good idea of how the topography changes in response to the trench being blocked, basically. At the beginning, so I'm running it, and at the beginning, when the trench is able to retreat, the mountain trend to collapse and the topography too. But when the trench stagnates, like it is the case now, whether it is during the flat slab steepening or after buckling phases, we see an increase of shortening and a significant uplift of the erosion. When underthrusting, then the Brazilian Tectonic shield, and when it becomes prominent, also, like we've said before, it leads to also a significant thickening of the erosion plateau through both ductile or brittle deformation. And by the end of the model, we end up with a landscape that closely resembles the present-day Central Andes, with and featuring a prominent forearc basin, but also an internally drained plateau where sediments also accumulate, as well as a prominent and active foreland. So what are the evidence, you might ask, about this slab buckling? I have here, for example, made a quick compilation of some previous study, and I have superposed the geodynamics model to, for example, here on the right, the regional model of 2003 of Liu. And on the left, we have also one of the most recent tomographic model from partner and co-author 2020, which extend down all the way to the mantle transition zone. And in both cases, we can observe a noticeable increase of seismic velocity near the transition zone, where it has been suggested a stagnation of the slab at shallower depth, so in the transition zone. Additionally, some tomographic model may suggest a potential slab remnant deeper, suggesting maybe a slab avalanche previous of 40 million years ago, eventually. Which could predate then the modern formation of the current Andes. Taken together, this observation supports the idea of slab buckling at depth. And interestingly, I later found out in the end of my PhD that the buckling idea was already proposed in two papers. This is a case of Lee and King 2011 here on the left. And SERPA 2014 and 15, where they suggest that the slab could buckle, but with a periodicity of around 30 million years instead of 10 million years that we have in our model, potentially explaining cyclical changes in the velocity field of the oceanic plate over geological time. And here I plotted additionally, I looked at the recent reconstruction of the plate velocity from Quero and co-authors 2022, and that also revealed a periodic signal here, the dash line in the absolute motion of the orthogonal plate motion, absolute motion of the oceanic plate. And this pattern that we observe suggests the idea of slab buckling and episodes of acceleration of the oceanic plate with a periodicity around 10 million years in this case. In fact, this acceleration appears to have occurred 3 or 4 times in the past 30 million years and is consistent with the proposed buckling periodicity that we have in our model. Overall, I suggest that the shortening rate is largely driven by the variation in the trench retreat, directly linked to the subduction dynamics, and particularly the free-falling and steepening of the slab during the buckling cycle. And another key factor to localize and intensify the deformation in the continental is the mantle lithosphere delamination that weakens the riding plate and allow to localize and intensify the deformation above it. But now let's have a look, a closer look at a present-day example of a flat subduction and how this change of slab dip may also have some effect on the deformation style of the foreland. And specifically, I will quickly focus on the southern Central Andes at the latitude of the Sierras Pampeanas and the Pampean flat slab, where the Pampean flat slab is currently being subducted here under the Sierras Pampeanas foreland. In this region, we observe the exhumation of crystal blocks directly above the flat slab, or more to the south, following the so-called thick skin deformation style. And this basically means that the deformation is well distributed in the upper crust, and that the entire upper crust is experiencing an intense tectonic activity. However, the mechanisms that are responsible of the change of deformation style in the foreland is not well or is poorly understood still. Here I propose an integrated view that links both the changing of geometry of the slab with the shift of the deformation style from thin skin to thick skin deformation style in the foreland. And this, together with Constanza Rodriguez Piceda, is a work where we have integrated much of her PhD into that, where she constrained the structural geometry and developed a thermal model of the lithosphere configuration of the southern Central Andes. And we have integrated all this data into a 3D data-driven geodynamic model, where we prescribe the plate velocity and compute the quasi-instantaneous solution for the deformational field in the continental plate. And this allows us to observe the deformation to develop in the riding plate in response to the change of slab geometry, and therefore help us to better understand this change of deformation style. And you can see in particularly how the temperature, for example, above the flat segment is cooling down, how the flat segment is cooling down the overriding plate above. And I will come back to that. So here are two different views of the resulting deformational field from our model. On the left, you have a perspective view showing the deformation of the Pampean flat slab beneath the overriding plate. And on the right, you have a map view. And here on the map on the right, I have overlaid in the Sierras Pampeanas some of the geological structures. You can see that the deformation tend to localize at the front of the orogen, where the slab is steep, and then progressively migrate toward the east when the slab is shallowing, and finally totally to the east when the slab is flat. This appears, and where the slab is flat, we have almost no deformation. Most of the deformation is actually well transmitted toward the eastern part of the Sierras Pampeanas, and this is due to, like I said before, to the cooling of the cooling of the overriding plate that prevents or inhibits the deformation of the overriding plate while transmitting the stress all the way to the eastern domain. Here, for example, with close to the Sierras Cordoba uplifted crystal blocks. And so this distributed deformation that we observe seems to resemble to also the deformation that we observe at the surface, where we have those uplifted blocks. So overall, this model result is analogous to what is observed, the observed change of the foreland deformation style from a thin skin deformation style at the front of the orogen to a thick skin deformation style in the Sierras Pampeanas. But we can also look at the velocity field, which indicate here in red how the velocity coming from the west is actually transmitted to the east from the oceanic plate far inland into the continental plate, where the slab is actually flat, and less pronounced or close, or where the velocity is transmitted in front of the orogen, where the slab is steep. And so in between those different areas, we have an area of transition where we observe here a dextral rotational component in the velocity field. And beside, I computed what should be the most likely deformation mechanism. So we have mostly frosting of the deformation is mostly expressed by frosting, but in the transitional domain, we have a bit of diffuse strike slip deformation. So overall, altogether, this defines a broad transpressional N-echelon shear zone forming at the leading edge of the migrating flat slab, where, and we refer to this mechanism as flat slab conveyor effect. And based on our model, we propose that the Sierras Pampeanas and the exhumed crystal blocks are the result of this transpressional diffuse deformation driven by the southward migration of the Pampean flat slab. So we propose that multiple roles of the flat slab in shaping the deformation along the Andes, first by intensifying the deformation at the leading edge as shown by this flat slab conveyor effect, and the formation of a transportational shear zone as in the Sierras Pampeanas region. Secondly, the cooling of the overriding plate above the flat slag segment strengthen the lithosphere, the continental lithosphere, and allow the deformation to be transmitted much farther inland, a process that was already proposed and often referred as slab bulldozing. And finally, as we saw in the 2D models, the flat slab also scrap and weaken the base of the overriding plate, which helps to enhance, to localize and intensify the deformation later on. From what we have seen, we can actually see that the Central Andes as a snapshot capturing the full evolution and changes of subduction geometry and dynamics from the before and after the passage of the Juan Fernandez hotspot ridge and the flat slab. From steep to shallow to flat, and eventually steepening again along with slab buckling in the central domain. This evolution is largely driven by the migration of the Juan Fernandez hotspot ridge, which increases the slab buoyancy, and by the long-term westward motion of the absolute velocity of the South American plate. And in terms of subduction dynamic, we propose that slab anchoring initiate or triggers the deformation in the Andes, as it was previously suggested by, for example, Fatchena and co-authors in 2017. And then a series of events, including the flat slab, but also the delamination, the free falling of the slab, the steepening and buckling of the slab, have intensified or pulsed the deformation, which allowed to widen and thicken as well as uplift the Andes. This process may mark a shift from an initial slab anchoring regime to a dominated slab buckling and free falling and steepening regime, and potentially in the future with the reduction of the plate velocity toward the slab piling regime, as we have seen in the previous slide. And in the next maybe 3 minutes before wrapping up, I'd like to take a couple of minutes to highlight how the Andes also provide a powerful lens for understanding the plate tectonic and planetary evolution. At the beginning of this presentation, we have discussed how the degree of coupling between the subducting plate and the overriding plate influenced by factors like a trench sediment influx and the water content along the plate interface can have a major effect on the shortening magnitude of the Andes. But this isn't actually just a local phenomenon. In my current postdoc, I'm exploring how the long-term change in sediment flux might have influenced the evolution of the global plate tectonic. And so as an experience, here I set two examples of global plate tectonic evolution model, both initialized around 1 billion years ago. So what you see here is actually the supercontinent of Rodinia, and as an experience in the top model, we will give like the same coupling that we have in the central Andes segment, while in the lower model we will give the interplate friction coupling that we have along the wall Andes. That is about 2 to 3 times lower than the central Andes segment. And so you can see how the model evolves. So it's a model, mental dynamics model, where we let the subduction and the model evolve by itself, and we end up with this configuration. So as you can see in the model with the central Andes condition, where the interplate friction is high, we are not able to develop a plate-like tectonic regime. In contrast, in the model with friction values that are representative of more of a global average or an average of the Andes, subduction can even reorganize to form a global network such as the ones that we observe in the Pacific Ring. Eventually, developing also a similar mantle dynamics that we have at present day, with most of the subduction, large subduction networks on one side of the Earth, and here we have plumes on the other side. We find that overall, in summary, when we apply specific condition of the central Andes to this global plate tectonic model, we find that plate tectonic does not emerge as it does under more global average condition at present day, coupling conditions. And this highlight of the central Andes represent a unique end member case in the spectrum of the tectonic behavior that we observe on Earth today. And I will finish on that. And thank you very much. And if you have any question, write it down in the YouTube section, and I can answer it today or even later on.
Thank you very much, Mika. It was so interesting to see the results from your PhD project, and also the new results from your postdoc project. So yeah, like Mika said, if you have some questions, you can write it down in the YouTube chat, and we can read it for you.
And since there is also a lag of time between YouTube and
yeah,
and that,
yeah,
maybe we need to
20-30 seconds. Now, one question now that I'm watching the final picture, that's one of your sketches in the field, right? In the upper part, I remember you were drawing in the strategy field trip. Those were so good sketches there.
Yeah, this was actually a sketch from Ornocal. I was helping Willeman van Koeken to map Ornocal, and then during a PhD, she did some thermochronology of this area.
Yeah, Mika, I have a question while we wait for if there's some of the people watching of the video. No, were you able to measure like for the slabs that are according to the seismic tomographies, like if you reconstruct or unfold the slab, it is consistent with the length of the slab that you will have, or the oceanic crust you will have coming from the Pacific side, let's say. Is it consistent with the estimated amount of plates, oceanic plates?
Yeah, so I mean, it depends how you see that. So since we get almost the right plate velocity, like it was shown before, but this is actually for I'm showing you how the plate velocity for a model that has no oceanic plateau here, and so no flat slab change over time following the bucklings, and how they might be almost. I'm sorry, I should show here. So how they might be consistent with this increase and decrease of activity of plate velocity that we observe from this paleomagnetic and plate reconstruction. So if you consider that this actually the match of plate velocity is somehow the integrated plate velocity is quite similar, then we should expect to have about the same amount of slab length. Another way to look at that is to take the tomography model, which was done in a paper 2019, southward propagation of subduction by, well, I will come back to that, but where they try to unwrap, taken the thickness of the tomography of the high seismic velocity and trying to unwrap, they define that, yes, there should be maybe 1,000 kilometers or more of a slab that should subduct. But it's not so easy, in fact, to determine how much slab has been subducted. So because this unwrapping from tomography model is very sensitive to the resolution of the tomography models themselves. So I will think that it's quite fine. Maybe in the model with oceanic plateau, we try to have lower plate velocity because obviously the oceanic plateau has a higher buoyancy, so it tends to slow down a bit more, like the subduction of the oceanic plate in our model. So, but overall, we are not far from what we should expect, I would say, from plate reconstruction.
Okay.
Yeah.
Okay. Thank you. Yeah, so we have some questions in the chat. So one from Lucas Fennel. So great talk, Michaël. I was going to say Michaël. Thank you very much. I have a question. Have you considered the sediment thickness in the trench as constant through time in your models? If it changed, will it have an effect?
So in the specific model, thank you for the question, Lucas. So in the specific model, we work directly with the effective friction. So we do not make the effective friction dependent on the thickness or strength of, thickness of the sediments above the oceanic plate. We set it as it is for an effective friction for frictional properties that were already defined for the Central Andes and the Southern Central Andes. We are working actually now that we have the coupling with surface process and climate working to look at how much sediment flux in this regional subduction model we should expect over time as we uplift the Andes. And these sediments flux with some porphyric pressure and with this amount of sediment flux and the increase of porphyric pressure will be computed in this model to vary the strength of the subduction interface. There is actually a work that is I was showing at the beginning of this presentation that mostly that is actually from Derek Neuhardt that's also started to look at this effect of sediment thickness into the strength of the subduction interface. And this is work done from ETH people. So yes, they can talk more about it. And we are trying to do it now with to do something similar with for the Patagonia case, where we have a quite efficient glacial erosion with Alexander Koptev and Guido Gianni. Yeah.
Okay. Thank you, Mika. And there's another question by Bernhard. So when you plot the hotspot track and South American plate, the hotspot is moving eastward and the South American plate not so much westward. Is that your modeling reference frame or just a plotting issue?
When I plot the hotspot track, so here I try to plot everything into like a mental absolute reference frame. So here we see the hotspot moving to the south. We see the plate, the South American plate that is also moving northwest. So in this case, like both motions of the plate are independent to each other, and so that's how we can see how the obliquity of the convergence may is actually what probably leads to the southward migration of the Juan Fernandez hotspot ridge. Was it like exactly the question? Because I maybe I didn't get like the end of the question.
No, so this hotspot is moving eastward, but the South American plate not so much westward. So, and the question was if it's your modeling reference frame or just a plotting issue. So.
No, it's in the absolute reference frame of the mantle, but this is actually from this nice paper of Joseph Martin in 2010, where he's rebuilding the motion of continental of the plate in absolute reference motion mantle frame, and explaining that one of the most important driving force of the shortening in the Andes is actually the westward absolute motion of the South American continental plate, and this absolute motion is that we are not trying to constrain in our model is is probably due to past subduction into and penetration of the slab into the lower mantle, which activate much larger convection scale and activate more important drag force at the base of the lithosphere. But this is maybe another topic, and it was something that was proposed by Adam Holt and so on. Yeah.
Okay, so Bernhard answers that, okay, the hotspot motion seems quite strong, but we can discuss this later.
Yeah.
We can walk across the to the other room. Yeah, but no, my question is, so it's not just like the hotspot; it's like all the ridge, like what you're plotting there, right?
Yeah, yeah. So this is actually the whole ridge. Yeah, like let's say the hotspot will be like the tip of this ridge, but like the ridge itself. So the hotspot ridge has been elongated, and obviously this is coming from plate reconstruction. So we don't fully understand how the deformation of the slab below may affect like this, the elongation of this ridge. So I mean, this is more like just a conceptual picture rather than something fully verified.
Okay, and we have another question. So the user is HD. Hi, Michaël, great talk. Do you think your model can be used to predict the current position of the subducted plateau? This would be an ideal tool to help seismologists to find this lost oceanic feature.
So the current position of the plateau, I mean, I will expect that the part that was subducted, I mean, the oceanic part of the oceanic ridge, or like the part of the plate that has higher buoyancy that was subducted 40 million years ago should already be at the base of the upper mantle, asthenospheric mantle, at least. I think also interestingly, and maybe this could actually explain in some way why, for example, it was proposed that we have, if I come back to the tomography, why we have maybe two blobs of high velocity zones. So we have one. So it obviously it will depend on the tomography models, but overall we can see that the slabs stagnate both at sorry, I should show you with my mouse, both at around mantle transition zone between 400 and 600 kilometer depth, but also are at between 800 and 1,000 kilometer depth. And so it could be that as we subduct like the oceanic plateau that is more buoyant and that lead to the stagnation of the slab at mantle transition zones, then this previous slab that was subducted slab to start to avalanche into the lower mantle. But because of the higher buoyancy of the slab, this pile of slab is actually remaining into the upper mantle. And it needs maybe more time to build more negative buoyancy for this pile of slab to then avalanche into the lower mantle. So I don't know if this will help, but I will expect that yes, like that past oceanic plateau that was subducted should be around like at mantle transition zone already at that time today.
Okay, so there's an answer from HD. I mean, in a similar way to Liu et al. 2010 in Nature Geoscience that found that the Shatsky Plateau beneath North America. This would be cool.
I mean, maybe we could just run a similar model adapted to the North American, but yes, that would be one way. Maybe we can talk about this in more details and yeah.
Of course. Okay, Mika. I think that was the last question, and so again, thank you very much for your talk, and it's nice to see the new model. So probably we're gonna invite you again after, I don't know, let us know when you have some cool results from the global models. So thank you very much again. Yeah, some people. Maximiliano Mercado, just the last question. A very interesting conclusion to have into consideration for many processes derived from magmatic activity. Thank you, Michael. I was going to say Michael and Michael like a whole talk. So sorry, Michael. But yeah, so let's talk. I don't know whenever you have new results. And thank you again, Mika.
Yeah, thank you for inviting me. And yes, I will be happy to make another presentation to show the global model results. Yeah.
Okay. Thank you gracias a la gente que estuvo escuchando la charla. Y bueno, vamos a avisar cuando sea la próxima charla dentro de ComTec. Thank you to everyone who was listening to the talk. We're gonna publish, I think, in our Instagram and also via email our next talk. Gracias.
Thank you.